Hello and welcome back everyone. So in this video we are going to learn about the concept of backbonding. It's a really important concept when you go on ahead with various other features. It's also required in resonance as we have already discussed while we were doing resonance video. It was a sixth condition. Okay, so firstly there are some conditions for backbonding. So let's talk about them one by one. So the conditions for back bonding are, your first condition is one atom should have lone pair electron. So one atom should have lone pair. Your second atom, okay. So one of the atoms should have vacant orbital, or where vacant orbital is basically vacant p or vacant d. Okay. We'll discuss about everything very soon, okay? And the third very condition of resonance is that of back bonding actually is that one atom should belong to second period element. One atom should belong to second period element. Should belong to second period element. We'll see soon why that thing is required, okay? So yeah, let's get ahead. Let me just slide down the screen a bit. Yeah, okay. So basically, what do you mean by, you must have got what is lone pair, right? How to get whether an atom has lone pair or not, so it's easy. You must have got how to get an atom, whether it's from second period or not, because it's just simply checking out your periodic table. And final condition is your vacant p. So how to check whether we have a vacant p orbital or not, or vacant d orbital or not. Let's discuss about that. So vacant p orbital. Vacant p orbital is when you have second period element with incomplete octet. Incomplete octet. So if in any case you have a second period element with an incomplete octet, then it has vacant p orbital. Okay. And how to check whether a compound is vacant d orbital has or not? So for vacant d, any compound which is above say third period or onwards have vacant d. All right, quite easy, right? So yeah, let's discuss a bit more about it. So basically, what is back bonding? So I'll show you one example. So what happens here is you have BF3. I'm going to draw the structure of it. So yeah, there is vacant orbital with this B, and you have fluorine which have lone pair electron. And so the conditions fills as this is second period element with incomplete octet, so it has vacant p orbital. This has lone pair, so the lone pair will be transferred to here, as you can see, and this will form something like a coordinate bond, but it's not actually a coordinate bond. So yeah, let's go ahead. So the major difference between coordinate bond and this bond is that uh, coordinate bond is a sigma dative bond. It has sigma, okay, and this bond is pi dative, okay. So yeah, let's go down and let's check out more. Let's do some amazing questions on top of it. So yeah, so what are the different cases that we can have is we can have first is 2p pi, 2p pi. So one pi electron goes to pi bond of another, okay, and 2 means second period. Then there can be 2p pi. We need one to be as 3 as second period, right? So one should be second period, and 3p pi. And the third can be 2p pi and 3d pi. So this is when the bond is formed between second period elements p orbital vacant p and vacant p and vacant p and vacant d. Okay, so back bonding basically results in a type of weaker pi bond. Weaker pi bond. Okay, you need to remember this pi bond, which is formed by sidewise overlapping between lone pair electron and vacant orbital. Hope you understood all of this, right? So let's do some amazing questions or let's start with very basic question. So as you can see, you might just say, what about CF4? CF4, does this undergo back bonding? So well, here one carbon has one atom has lone pair electron, but the other atom, if you check out, don't have a vacant orbital. No vacant orbital. So there is no back bonding. Understood, right? Let's go down and check out more. SiF4. Check out the example of SiF4. So, so there is another thing. See, SiF4 is somewhere like this. So yeah, let's start with the lone pair. Yeah, we have lone pair. Second, do we have vacant P? No, because it has complete octet. But we still here we have vacant d orbital actually. Vacant d orbital because, as you can see, the silicon comes from third period, so it has vacant d. Okay. So for overall structure, you can draw it like this. This is also a type of resonance. Back bonding is a type of resonance. I have discussed it in my resonance video. So yeah, you can check it out. So you can draw the overall structure like this. Similarly with BF3, but I'll give you another example of CCl3 minus. So let's check this out. CCl minus. If you see here, this chlorine have lone pair, but you can see carbon belongs to second period element, so it cannot have vacant d, and it has complete octet because 2 4 6 8, so it cannot have vacant d. So you might think no vacant p or d, right? So you might think there is no resonance, but there is back bonding here. Where? So I'll show you. The back bonding here is between, as you can see, negative charge is also considered as a lone pair, and chlorine is from third period element, so back bonding will go this side, okay, not that side, what you were expecting. All right. So yeah, let's check out few more concepts. So due to back bonding, your bond length always decrease. Okay, always decrease. Why so? Because it gets a pi character, right? It gets a double bond is shorter than single bond, and it's somewhere around in between of that, right? So your bond length always decrease. You need to remember that. There might be questions on bond length regarding this. Okay, and if your central atom receives electron, regardless, its hybridization will remain same. Okay, hybridization will be same. Hybridization will remain same. Will remain same. Okay, hope you understood it. So this is an important point. I have my notes actually with me. So yeah, and due to backbonding, central atoms uh, even hybridization can change sometimes. So yeah, let's look at that. So BF3 case, we learned how it is. So backbonding, before backbonding it is sp2, and even after backbonding it is sp2. Okay, after backbonding. And let's check out another example. And if central atom denotes a lone pair, if your central atom denotes a lone pair, as we saw in the case of CCl3, then its hybridization will change because your central atom is giving the electron, so that electron is delocalized, and we do not count delocalized electrons in hybridization. If you want to learn more about it, you can go out and check out my video on resonance part 1, where I've discussed about why delocalized electrons are not counted as in hybridization. So in hybridization, normal formula of hybridization is bond pair plus lone pair, but these lone pairs should be localized, not delocalized. Delocalized lone pairs are basically which take parts in resonance. Okay, here in this case these lone pair are going to chlorine, so yeah, the hybridization can change, but in this case it is coming from fluorine, so hybridization won't change at all. Okay, you understood it. So such as the case of NCH3 CH3 CH3, here if you see before hybridization the hybridization is sp3, but after hybridization it will be sp2. Okay, so yeah, so what else do back bonding help us in? Back bonding help us in the idea of acidic nature of a compound. Acidic nature of a compound. So how does it help you in knowing whether a compound is more acidic or not? So yeah, BF3, BCl3, BBr3, Bi3, all of these are Lewis acid. Why Lewis acid? Because they have incomplete octet, so they are electron acceptor, isn't it? Yeah, but due to back bonding, BF3 will show back bonding here, and your BCl3, is there any back bonding in BCl3? Yeah, same back bonding here. But usually what happens is, as we keep on going ahead in the row, back bonding almost become not negligent, because 2p pi 2p pi back bonding is most stable than the next ones as we go down, 2p pi 3d pi or 3p pi or 4d pi or whatever. Okay, so the order of acidity as per, because of the concept of back bonding, would be this way. Why? Because now the tendency of accepting electron due to back bonding decreases, because it is getting electron from fluorine, right? So it is a less strong Lewis acid. Hope you understood this concept. Similarly, if you see the concept SiF4, SiCl4, SiBr4, and SiIF4. So here, if you see 2p pi, 3d pi, right? So what happens is, like, due to back bonding, as the back bonding tendency increases, electron deficiency increases, right? So therefore acidic character decreases. So similarly you can do this well. Okay, and usually back bonding is not considered after 2p pi 3d pi, as we already saw. So these fourth period element and fifth period element won't even have any back bonding. Okay, yeah. Here in this case you might see, firstly, this case, this, it goes this way, and now you might say, why there is a back bonding? There is no back bonding firstly here in all of these compounds, because both are third period, and we need at least one to be second period, which was there in this, but still it was negligible. So there is no back bonding in these compounds, so we can directly see which one is more electron accepting and which is Si. Okay, Cl4. But if we compare between these two, why this one has, even after having back bonding, why is it better Lewis acid? So it is because here your minus inductive effect of fluorine. So fluorine will be pulling out electrons, right? So inductive effect of fluorine is much higher than your back bonding. Okay, as we already learned that back bonding is a weak way, so you need to remember these specific examples. Let's get ahead. Let's go down. And if back bonding, so now we need to generalize the thing. So how to know where my inductive effect or minus I effect is more dominant? So if the back bonding is between 2p pi and 3d pi, 3p pi actually, 3p pi, then inductive effect is greater than back bonding. Okay, whereas in the 2p pi section, there was not such thing, right? And due to back bonding, there is another first we learned about your bond length. Now we are learning about our bond angles. So due to back bonding, either your bond angle remains same or increase, but back bonding don't decrease your bond angle. So as in case of NF3, okay, this has lone pair. Yeah, but the thing is, this is lone pair, so it has complete octet, so there is no back bonding. Okay, whereas in case of NCl3, there is back bonding, right? Yeah, this lone pair can go to this D. It has a D. It has incomplete D orbital, right? Okay, so yeah, this lone pair can go there, and which will lead. And this is also a very explosive compound. You'll learn about this in your P block. Okay, and so back bonding can happen, but in this special case, no back bonding is considered. Okay, so you need to remember this is special case. Back bonding can happen, but we don't consider it in this special case. There's another example. Let's go with that. Is you need to remember, if you want to take out notes with me, do take out these special examples. You won't find it anywhere in even a lot of coaching's material or anything. Okay. So yeah, in this case, back bonding is present as we learned, and from C to Cl, right? So the same way this carbon or electron is in this two back bonding is present from C to Cl. Okay. So as we learned about bond angle, that how back bonding can, did we learn how back bonding can change your bond angle? Well, let's check that out. So actually, I have another separate video. I'll post another video on bond angle concept. So how to compare bond angle between different compounds, and I have a step-by-step process that you can follow, and you will literally never miss any question around bond angle. So I'll figure that out. I'll talk about that in that video, but you need to remember one thing for sure, that due to back bonding, your bond angle either increases or remains same or increases, but never decreases. Okay, same or increases, but never decreases. So yeah, I hope you enjoyed this video, and I'll see you in the next one, maybe where we'll be discussing about bond angle. Take care, have a great day.